Alright, in this video we look at a line integral of a vector field. That is this particular notation right here. This is a line integral of a vector field f that has been given. Okay, so you can see that the vector field, this notation is good. It tells you that you have to have a vector field as your some starting data, and you also have to know some information about your curve or your path of your integration. Okay, the meaning in this video, we're just going to focus on notation and doing the mechanics out. But the notation says that this line integral of a vector field f, this would be the dot product dr, that this means, or the notation means, that you need to do a line integral from t is equal to a to t is equal to b, where a and b are the times that define the endpoints of the path or the curve that you're moving along. So you need to have a parametric form of your curve. Okay, so you will then need to find the vector field along that path. So at every point along the curve, you need to find what the vector field or the arrow looks like at that point along the path. Okay, now this vector field doesn't have to be a tangent vector field. It doesn't have to point in the direction of the curve, but the vector field can just be whatever the vector field is. It doesn't have to have any sort of relation to the curve itself. It just has to be vectors at the points on the curve. And then you bring in the curve itself by doing the dot product with the derivative of the curve, and r prime at t is the direction vector of the curve. Now this vector field does have something to do with the curve itself. It is the vector that is pointing tangent to the curve. So it's pointing in the direction that the curve is going. Okay, so we have these two vector fields, the vector field itself given by the vector field f, and we also have the direction vector field of the curve. And we will then want to compute the dot product. You'll want to compute this dot product of those two vectors and then integrate the resulting scalar that comes about from that dot product, and then you will need to evaluate that integral to a number. Okay? Essentially what we're doing here is we are thinking in terms of units that the vector field f is, think of a force vector field. So this might come out to have the units of newtons, the force. Okay? We know that the units of r prime at t, r prime is the velocity vector, so this might have the units of meter per second. And dt is equal to time, so this might have the units of time, seconds. So when you look at r prime at t dt, okay, this is what we call dr, r prime at t dt, that will have the units of meter per second times seconds, which will have the units of meters. And then when you do the dot product of the force dot product with r prime at t dt, you will have the units of Newton times meter, which is a unit of work, a force over a given distance. So these integrals, these line integrals of vector fields, are sometimes called work integrals, and we will discuss a little bit more what the dot product is doing, why we need a dot product. But let's just work on some mechanics here, and we'll look at an example and see what's happening. Okay, so here are the steps when you have a line integral, okay, of a vector field. Here is the definition that we just went through. Here's its definition. And here is the notation that indicates that line integral of a vector field. And so here are the steps that you need to go through, right? You need to parameterize the curve. You need to know what the curve is as a vector valued function in one variable. You need to parameterize it. You then need to, at step 2, find the velocity vector. Okay. Step 3, you'll need to find the vector field along the curve. So there's a vector field along the curve. Then there will be a pink arrow, which is the direction of the curve. And then we'll need to compute this 1D integral, and that will involve looking at the vector field and the dot product with r prime. And so by doing this dot product, we're essentially doing a projection of the force onto the direction of motion. So we're looking at how much of the force is pointing in the direction of the velocity vector. And it is only that part of the force, the component of the force pointing in the direction of the curve, that contributes or does the work. So that's what we're going to do in step 4, is to compute this integral by doing a dot product to project the force in the direction of motion, and then we will add up the contribution of that force over a given distance, and the resulting number is the amount of work done by that force in moving a particle in the given direction of the curve. So let's get to an example now. Those are the steps. Let me show you that one more time so you can write it down if you need. So here is an example just to kind of get all the mechanics worked out. We're seeing that here the direction is important. Here we have a curve. The curve description is that we have a line going from the point -2, 1. I'm sorry, -2, -1. Right, so there's a point P, -2, -1, and we have a line going to the point Q at 2, -1. So the direction is important here. We have a curve going in this direction. Okay, so we're going from the point P to the point Q. Okay, and we can see in the background here that we have a vector field given. So here's our vector field. Okay, and specifically we have the vector field at the points on the curve. So these arrows right here are the vector field along the points on the curve. There are a lot of points in this vector field, but to do a line integral, we don't care about those vectors. We care only about the vectors that are at the points along the curve. Okay, so if we were going to do a line integral along this path, which is going from P to Q, and we have this direction of motion, and we have a vector field underlying that problem, which is kind of pointing to the left if x is negative, and pointing to the right if x is positive. So we have a vector field that is given as x, 0. And we have a curve that is a straight line. It's a line from the point P to the point Q. And from there we should be able to compute a line integral of this vector field along that curve. And we will integrate from some time up to some other time. We need to figure that out. We need the vector field along this curve that we come up with. We need to dot product it with r prime at t, and then we need to do a dt integral. Okay. But our curve is just a straight line from P to Q. So we know the equation of a line from between those points. We have that the point P is -2, -1. plus the direction vector from P to Q multiplied by T. But the direction vector from P to Q is Q minus P. Subtracting these 2 points will give the vector. Okay. And so that should give us 4, 0. Okay. The vector from here, point P to point Q, is just 4 units to the right, 0 in the y direction. So we have our parametric form of our line is -2, -1, plus 4, 0 times t, otherwise known as x is equal to -2 plus 4t, y is equal to -1. Okay, so when we look at our vector field along the curve, right, our vector field along the curve just says that we need to plug in x is equal to -2 plus 4t and put y is equal to -1 in this vector field wherever you see the x and the y. So since our vector field is x, 0, the vector field along the curve is -2 plus 4t, 0. And then the direction vector, r prime of this curve, is just the vector pq, so that is 4, 0. Right? And because of the construction of this line, we can say that at t is equal to 0, we're at the point P, and at t is equal to 1 second later, we're at the point Q. So we're going to integrate from 0 to 1 of the dot product of the vector field and the velocity. So we have the integral from 0 to 1, okay, and then when we do the dot product of the vector field and the direction vector, we get -2 plus 4t multiplied by 4, okay, which is equal to let me just pause this video for just 1 second because I was expecting to get the answer 0, but give me 1 second. Alright, we're back. So sorry, it was hard for me to see to the end of this problem while I was writing and talking at the same time, but we can see that if you actually do evaluate this integral because of the -8 plus 16t, when you integrate you'll get -8t plus 16t squared over 2. So integrating from 0 to 1, that you actually do get 0 for this answer, which is the same thing that I got up here. And this brings up an interesting point that there is more than one way to parameterize this curve. So here we did x is equal to -2 plus 4t, y is -1, and we integrated from 0 to 1. But up here in this example, I also wrote the curve as t, -1, and then that is the same thing as the same curve if you integrate from time -2 to +2, right? So what we're finding here is that these integrals, these line integrals, will give you the same answer no matter how you parameterize the curve, which should be a reassuring idea that the answer is not dependent on coming up with the one and only parameterization of the curve from P to Q, because there are an infinite number of those, so that we get the same answer no matter which parameterization we pick. Okay. Now, so we get 0 as I kind of suspected, and I suspected that because of the nature of the picture. So let me just bring up this picture and let's look a little bit more closely at why we got 0 for our answer. Okay, so here we're seeing in the black arrows, we are seeing the vector field itself. Okay, here's the vector field. And this vector field, depending on the value of x, is pointing to the left or to the right. Okay, so at the points along the curve, red is the curve, we have a vector pointing to the left and to the right. Okay, and our direction of motion, right? We're moving along this curve. We're always moving to the right. We're going from the point P to the point Q. Okay? So it's very important when we do these line integrals that we do the vector field along the curve dot producted with the direction vector of the curve. Okay? And here we can see that sometimes the vector field is pointing in the opposite direction of the direction of the curve. And because of the nature of this dot product, you'll recall that there's an equivalent definition for the dot product, that it's the magnitude of the force, magnitude of the velocity, times the cosine of the angle between those vectors. And here we can see that the angle between the force and the direction of motion is equal to 180 degrees. All right, so the cosine of 180 degrees, or pi, is equal to -1. So here we can see that the direction of motion being 180 degrees is that the force and the vector field are the vector field and your direction of motion are opposing each other. So that's in a sense a negative work. But once you get over here to the other side, right, we can see that the force vector and our direction of motion, that the angle between them is equal to 0. They're pointing in the same direction, so that the cosine of 0 is equal to 1. Okay. So what we have here is for half of the why is that? Okay. So for this half of the motion, as you're moving along this curve, the work is less than 0, and on this side the work is greater than 0, and it's the same amount of work because the force was actually equal to a constant, except up to direction. So that's why I expected the work to be equal to 0 in this problem, because we had the same amount of work done but equal in opposite directions. So ends this video on computing an example of a work style integral.